let's come back. Well, before I forget, did Yogev Becker ever show up? Yogev?
He's on vacation.
Okay. All right. I want you to know I'm going to be on vacation next week, but I'm going to be lecturing from my hotel room. I told my wife that I got to, I'm going to we're going to break out Tuesday, and she can go do things on her own, and I'm going to be giving you my lecture from my hotel room where I'll be next week. So you'll have a different change in background scenery, but lecture will still be the same.
I think it's a mistake. She's going to spend a lot of money.
Yeah.
Oh, great.
I kept changing my my plans instead of going to Israel, which Israel won't let me in, and then I made a few other plans that got changed from coronavirus. So this is the last chance before my my university academic semester starts, which is right after your class. I start my other class, so I'm going to go back to back.
Anyway, have fun.
Thank you. Okay, so let's share our screen. Where were we? Okay. So now we're going to get to what I consider to be the fun part of the lecture, because I'm going to get to start showing you all sorts of nasty pictures of things, of defects. Okay, so there we go. So we started talking here about the surface. Let's start with the surface damage that you see right over here. This goes by a lot of different names, but the most common name used these days is called rolling contact fatigue, or RCF. You'll also see the same phenomena referred to as head checking or spalling. And what we're talking about are these. These micro cracks, which grow into spalls and larger cracks, this is rolling contact fatigue. This is always on, or almost always on, the gauge side of the high rail. So the inside, gauge side being inside the track, part of the high rail, where the wheel runs against the rail. And guess what? Single point contact, maximum high contact stress, all those nice things I've been talking about translate into RCF, or rolling contact fatigue. So hairline cracks appear at the gauge corner of the rail, which grow large in the hairline crack. Usually they're at an angle. If you look over here, you'll see that they're not normal to the rail, but they're actually at an angle. And the angle varies depending on the relative amount of longitudinal lateral slip. So what you're actually seeing is shear. You're seeing a slip plane being developed between the wheel and the rail. And the result is this rolling contact fatigue. Its initiation is hard to see, but you can almost always feel it. And it's maintainable. We'll talk about maintenance in a little bit, but it's more, this by itself looks pretty ugly and looks pretty nasty. And here's another view of it. You can see sort of a piece is starting to break out. This by itself is not what I would call catastrophic. This by itself results in a potential for catastrophic. And again, just show you a few more. You can see the angle of the plane with respect to the train running direction. Okay. So what can happen is you can develop underneath this spalling, or underneath this rolling contact fatigue, you can generate subsurface shelling. So here you can start seeing the subsurface shelling. So subsurface shelling is a defect that falls underneath that rolling contact fatigue, that propagates longitudinally. And here you can sort of see the collapse of the rail underneath that shell. Here you can see a shell that breaks out. And again, you can see the size of the breakout in the shell. There's again the surface that broke out. But
By micro cracks, you mean crevice? Crevice are micro cracks?
micro cracks are depending on the size. So you're dealing with micrometers instead of millimeters. And
So what is crevice? What is crevice?
crevice usually refers to something a little deeper.
Okay.
In the normal application, a crevice is a deep crack. The rolling contacts fatigue starts off with very shallow cracks. And in fact, there's just now technology being developed to measure it. There are eddy current measuring systems out now that actually allow you to get the depth of the crack. And Israel Railways and many railroads have been developing guidelines for when it's appropriate to come in and grind these out before they develop into something more serious. And the more serious is this: the detail fracture from shell, the Hatfield derailment. So the detail fracture from a shell, so this is the sequence that you deal with, and it's not everyone, but it's enough of them that becomes very serious. You start off with your micro cracks, which are you can see the micro cracks are barely visible. Then you go into your rolling contact fatigue, spalling surface cracks. That in turn translates into some shells, and then that turns transverse. So the shell is running along longitudinal distance of the rail along this direction, and then all of a sudden it starts to turn transverse, and it grows across the rail section like that. So this is a detail fracture from shell. This is what happened at Hatfield. This is one of the largest, if not this is the largest category of fatigue defects that are found in welded rail. Putting joints aside, we'll talk about joints later. But in welded rail, this is the largest category of fatigue defects. So this is a progressive fracture, which means it grows. And it grows from a railroad point of view very quickly. So remember, we're talking about the life of the rail being 1,000, 1,200 million gross tons. To grow from barely detectable to about to break for a detailed fracture is of the order of 25 million gross tons. So if it's a 50 million gross ton railroad, that's 6 months. If it's a 100 million gross ton railroad, that's 3 months. If it's a 10 million ton gross ton railroad, that can be 2 years. So depending on how your density is, depends how much time you have to go in and detect it before it breaks, which becomes a whole issue of risk management. And it's a whole other topic area, which I may not be able to get to in this class. So as I said, it usually initiates, there's a good picture of one. So it usually initiates from a shell up here, very often the point of maximum shear failure of the rail. And then it grows transverse. You can see the growth rings on it. And then when it gets large enough to weaken the bending strength of the rail will literally fracture under the wheel. And that's exactly what happened in Hatfield. It kept growing. And then at one point, the rail got weakened to the point where a good dynamic wheel load, probably associated with the wheel flat or something that gave it a little bit of extra oomph to that dynamic force, fractured the rail. And then you had a derailment. Now, as I said, the good news is 99.95% of these are found before they fracture. The bad news is 0.005% of them are not. Oh, no, 99.99% are found before they cause a derailment. About 90 to 95% are found before they fracture. Another 5 to 9% are found after they fracture, but before they cause a derailment, such as when they interrupt a red signal out there and stop trains from going across it. And 0.005% of them actually result in a derailment. So here's another picture of it. There's the real one. There's a little bit more visible one. Again, you can see how it's starting at this point of maximum shear strength, then how it's growing transverse. Now, this is one of my favorite pictures, because if you look really closely, this defect never breaks the surface of the railhead, which means if you're walking down the track, you can't see this big monster. This monster is a fracture waiting to happen. The fact that it didn't break was just somebody's, one railroad got super lucky. But once, this fracture is about a 90% head area fracture, and it's totally invisible from the surface of the rail. Only way to find is by ultrasonic testing. Okay, so these are a detail fracture from a shell. They all initiate at a shell, usually under rolling contact fatigue, usually on the gauge corner of the high rail. And by the way, we see them, as I said before, we see them in freight railroads, we see them in passenger railroads, we see them in metros. So these are found everywhere. A relative of this defect, but a different defect, is the transverse fissure. Now, when you look at this, it sort of looks the same, but it doesn't start at a shell up here. It starts at some sort of initiation point, nucleation point over here. So here's a better picture of it, showing the nucleation point. In this particular picture, this is a hydrogen inclusion. This is a concentration of hydrogen that was trapped in the rail manufacturing process. Now, the good news is, as we've been moving to a manufacturing process called clean steel, which was adopted in the late 1990s, these defects are decreasing in seriousness, because these inclusions, these imperfections or impurities inside the rail steel are being gotten rid of by the clean process. Not totally eliminated, but gotten rid of. So the transverse fissure from an inclusion has gone from being a very common defect to being a rare defect, whereas the detail fracture from shell is not initiating at an inclusion, it's initiating at a fatigue initiation point associated with high stress. All that nice math that I've been throwing at you before translates into the development of these fatigue defects. But they're not the only ones. We have a whole class of different fatigue defects that we get to play with here. We have the horizontal split head. Now you see over here, this is a horizontal defect across the railhead. And it actually propagates longitudinally. It's usually about 6 millimeters below the running surface, and it propagates in this direction. And when it gets large enough, a whole hunk of the rail breaks out. I got a picture of that? Yeah. So a hunk of the rail breaks out, and you also usually you'll get a transverse fracture as well. So here you can see the horizontal split head still propagating along. You can look over here on the side of the rail. You can see how long it's extending, and you can see how a piece broke off here and then fractured the rail. Okay. A cousin of the horizontal split head is the vertical split head. Vertical split head is also a fatigue phenomena. In fact, the vertical split head is emerging to be the #2 most common fatigue-initiated defect in welded rail territory. Detail fracture being 1, vertical split head being 2. So you can see a vertical split head, the crack is vertical rather than horizontal. This is showing at the middle of the railhead, but it doesn't have to be the middle of the railhead. It could be over here. It could be over here. And in fact, we know that when we change wheel rail contact loading, we actually can shift the location of vertical split heads. It likewise propagates longitudinally and then breaks out sideways. So I have a broken piece of rail coming off to the side. Here's a vertical split head that's grown a bit, but it hasn't yet broken out. You can see how it's starting to break out. You can see how the crack is propagating here. All I need is the crack to propagate over here, and this whole piece will disappear. And then if I go around and my wheel flanges over here, I have a derailment. Now, I laugh a little bit because some of the manuals say you can see a rust streak underneath the head close to the web. That's over here. And I know railroads that used to do mirror inspections here to try to find the rust streak. But I'll tell you, I've been inspecting track for the better part of 40 years, and I would not trust myself to find one of these. I'd much as rather rely on effective ultrasonic inspection. Okay. Now, I said detail fracture and vertical split head are among them are the most common defects. In certain locations in Europe, the squat is the most common defect. So what's a squat? A squat is a defect that initiates in the center of the railhead and then propagates, as you can see, at an angle, and then can turn transverse down. This is called a Tascheval branch, and then propagate all the way down and fracture. Or it doesn't have to propagate all down. I get a heavy enough wheel load, this will just fracture at this side. So this is a squat defect. Starts off growing at a flat angle, and then will branch. So you have this one coming here, and then this one going down here at a much sharper angle. And it can actually initiate at any angle through the rail, but it usually starts off shallow. This is usually 5 to 10 millimeters before it splits and then branches downward. Compound fissure is a combination of vertical and horizontal defect, as you can see over here. You can see the vertical and horizontal. So this is sort of in three planes at once: vertical plane, horizontal plane, and longitudinal plane. Here's a fractured compound fissure. Again, you can see the horizontal, longitudinal, and the vertical component to it. Another interesting defect is the head and web separation. So the head and web separation is a failure over here. Interestingly enough, we see a lot of these in level crossings. And this can grow to be lengths of several meters in length. And then at some point, the whole head will pop out. You can see how it propagates longitudinally. And as I said, at one point, the head will break out. An ordinary break. This is often associated with a stress concentration factor. So if you look down here, you see this dent over here. Very often associated with a guy with a sledgehammer or a spike maul or some sort of, or even a tamper. I've even seen tamper damage, even though it's less common with a tamper, causing a stress concentration on the base of the rail, which multiplies the stress, and then the defect will propagate vertically through the rail without any sign of a fatigue defect per se. It will just propagate. It will be a crack propagation through the rail. Rail surface defect, engine burn. This is another fairly commonly found type of surface defect. Very often see these on grades where, as I indicated, the locomotive barely has enough power to go up the grade. So if something interferes with it, most likely rain or grease or something on the top of the railhead, the engines spin. The axles, the wheels spin, and there's an engine burn. There's usually a mating engine burn on the opposite rail. So on the opposite rail, because the axles are rigid. So if this wheel is spinning, the other wheel is also spinning because it's the same axle, and you'll get a burn on both sides. This is what it looks like up close. These can be easily 12 to 20 millimeters deep. But even worse is that you can develop a defect underneath the engine burn. And what's particularly nasty here is the engine burn will hide that defect. So if I have a railhead, and if I have a defect over here, and I have an engine burn over here, I won't be able to see this defect with my ultrasonic test, because my ultrasonic test will find this engine burn and say, hey, you got a nasty engine burn over here, and not penetrate down further below the engine burn. Now we come to my all-time favorite type of defect, first defect, because it is one of the most pervasive types of defects around, is the surface defect, and that's rail corrugation. Rail corrugations are waves in the surface of the railhead, and they're found in everybody. Heavy axle load freight, light axle load freight, passenger, metros, light rail transit, high-speed rail. Everybody sees rail corrugations. It's associated with wheel rail dynamics, noise. In metros, they call it roaring rail, because it makes such a noise. It induces undesirable vibrations, which means it gives you poor ride quality, and it generates very high dynamic impact forces, which can break things. So here's a view of a corrugation down the railhead. This is one of your more standard type of passenger type of corrugations with a uniform wavelength. So let's define a few things. Wavelength is defined to be the peak-to-peak distance of a corrugation. It can also be valley to valley, but usually it's easier to do peak-to-peak. So it will be this distance to this distance will be my wavelength in millimeters. The depth of my corrugation is my top of my peak to my bottom of the valley. So I would say put a straight edge across the top and measure from the top down to the bottom of the valley, and that total distance is the depth of my corrugation. So those of you who think in terms of sine waves, it's twice the amplitude of a sine wave, because the amplitude of a sine wave is from the median, but the depth of a corrugation is from the peak to the valley. Why? It's the amount of metal you have to remove to get rid of the corrugation and surface. And how do you remove the metal? By grinding. We'll get to that. Okay. I break up corrugations into 3 broad categories. Other people I know break it up into 7, 12, 15. I have a book called The Art and Science of Rail Grinding, which really talks about rail grinding. I know Israel Railway has several copies of it. I'm not sure if any of the metros have copies of it. There's an entire chapter, though, devoted to rail defects alone, and it shows several different definitions of corrugations. So very quickly, the 3 broad categories are roaring rail corrugations, which are also called very short wavelength corrugations, where the wavelengths are of the order of 25 to 75 millimeters. So that's your peak-to-peak distance, 25 to 75 millimeters. Shortwave corrugations, which you see more in freight railroads, and they're about 75 to 300 millimeters. And your long wave corrugations, which are 300 millimeters to 1,000 plus millimeters, we see in high-speed rail. We actually see these in lower speed rails, but quite honestly, the wavelength is so great, they don't cause any problems at lower speed. But at higher speed, with your frequencies come down, and all of a sudden, this very large wavelength becomes a serious problem. All of them make noise, but the metros are notorious for making lots of noise, particularly in an underground tunnel. The underground tunnel, the noise is amplified by the walls of the tunnel. And so you get this roaring rail effect, and that's why they're often called roaring rail corrugations. So here's another view of the corrugations. This is, you can see this is a relatively short wavelength corrugation. So, if you say this distance here is what, 300 millimeters? No, more than that. This distance here is about 600 millimeters. So what do I got? I got about 10, 15 corrugations between sleepers. So I say 15. So 600 divided by 15 is what, 40 millimeter wavelength. So that would fit me into the shortwave corrugation definition.
They appear only in curves?
No, we see them on tangents as well.
Okay.
In metros, for example, we often see them on grades, on tangent grades. We also see them in places, I'll talk about this in a minute, but we see them in places where there's a change in track stiffness. So I'll come back, let me come back to that. But yes, we see them in straight track as well as curves. So here's an example of a shortwave corrugation where again, you see the definition of the wavelength and the definition of the depth. Here's a shorter wavelength corrugation. You can see sometimes they're very difficult to see. To catch a corrugation like this, you have to just get the angle right. You have to look down the track and see it. If you're looking straight down, very often you see this or not even this much. You can see this is a longer wavelength corrugation. This is maybe what, 60, 70 millimeters? Actually, yeah. And also you see this is a variable wavelength. You can see this wavelength is not the same as this wavelength, is not the same as this wavelength. Whereas this is a pretty constant wavelength. And we see that too. What we see is on the roaring rail corrugations, we see the wavelengths are very uniform. In the short wavelength and the long wave corrugations, we see this variable wavelength, a variable pitch that you see in this picture. You also see it here. You're going to get now. Notice another thing to notice is notice the texture, the shape, the behavior of the corrugations change. The short wave range corrugations are very smooth. The longer wavelength corrugations start having fatigue damage that is a little bit more evident. You still see the pattern. You can see these corrugations spreading down here for, hundreds of meters, if not a kilometer or so. And you can see this is in a tangent leading into the curve to answer your other question. Again, you can see the difference in mechanism here and here. So if you look at the distribution of wavelengths for the roaring rail of very short wave corrugation wavelengths, they tend to be a very narrow band. For this type of corrugations and this type of corrugations, they tend to have a more greater distribution. Now, the obvious question is what causes corrugations? And the short answer is we know it's a wheel rail dynamic mechanisms, but there are as many theories of corrugation development as you can wave your hat at. There are at least 3 dozen different theories of corrugations. For example, the British came up with a theory a number of years ago that it was a differential wear, that there was a work hardening at the peaks and a softening at the valleys, so it wore down at the valleys, then hardened the peaks. And they came up with nice hardness traverse measurements that proved it. And then the Americans at FAST, at the major research facility in Colorado in the United States, tried to duplicate the British behavior, and they found they couldn't even come close to it. They were getting much more uniform hardness all across the railheads and the peaks and the valleys. So there are lots of theories, and so the answer is we're not 100% sure, but we know it's dynamically induced. So for example, you notice this is wooden sleepers, this is concrete sleepers. You notice there's a very, very, very nominal amount of corrugation here, and there's a much more dramatic amount of corrugation here. And we see this all the time. We see this in metros, where you go from a slab track to a ballasted track. If you have a transition from ballasted track to slab track in a metro, we very frequently see corrugations develop at that stiffness transition. So the theory is that that difference in dynamic response when you get to a stiffness transition causes that development, that more rapid development of corrugation. And we know we see more rapid corrugations on stiffer track than we do on softer track. The long wave corrugations, as I mentioned, they're things that we see in the high-speed rail. I remember going to Amtrak in the 80s. Okay, so this goes back a long way, and saying, you have corrugations between 0.5 meter and 1 meter wavelength. They said, you're crazy. Look, we don't see anything. There's nothing out there. And I remember I built a 0.5 meter straight edge. And I went out to the railroad with the people and I said, here, look. And lo and behold, the wavelength was very, very obvious under that straight edge. It was only of the order of maybe 5-10 millimeters in depth, but it was very, very, very real and very significant. Now, why are corrugations bad? Well, number one, they cause a lot of noise. Number two, they cause a lot of vibration. Number two, they cause nice impact forces. So this is wheel rail contact force as a function of corrugation frequency and corrugation depth. And the point of the exercises here is that there is if you have corrugations that are of the order of 1 millimeter deep, you get a factor of 2.5 to 3 times your static wheel load associated with that corrugation. This is for wood sleeper. This is for the same analyses for concrete sleeper with a much stiffer modulus. And here you get 3 to 3.5 times. So we very much see a stiffness effect here. There's also a speed effect. We know corrugation dynamics increase with speed. And we also know that corrugation grow in a nonlinear fashion. So the rate of growth early on of corrugations is relatively low. And then as the corrugations start to materialize, the rate of formation increases and more rapidly. We also see energy loss. So let's go back to this pic. No, let's go back to this picture. So you're a metro or you're a passenger rail and you're running along this. Imagine what's happening to your wheels. Your wheels are vibrating, right? Not only are they generating a dynamic force, as we saw over here, they're actually dissipating energy. And we know from analyses and tests that the energy loss in corrugation track is more than double the energy loss on track with just regular defects. and maybe 3 times as much track with virtually no defects. And in terms of how much it is, in this particular model, normal energy loss for normal train operations was about 40 watt-hours per ton-mile. Sorry, the units are in English. The corrugation loss is about up to about 12. So it's what, about 30%, which is very significant. It's a very significant energy penalty. Okay, other type of defects. Let's get back to the sort of the more common type of defects. We have the battered welder joint. Well, I have a weld. Remember, we said the welds are softer than the parent metals. If I have a joint, I actually have a physical discontinuity between my rail ends. My dynamic forces will batter these down and result in a surface degradation. So if I have a weld, you can see my weld clearly here. Notice I get the start of weld batter here. Now, anybody want to tell me why the weld batter is not here, but why it's here? I did allude to it a little bit earlier on, but it was something that I said very quickly in a previous lecture.
Because of the influence of the temperature.
Because of the heat affected zone, right?
Heat affected zone.
The heat, exactly. That's exactly right. When you weld, remember you put a mold over here and you have that very high temperature out here. Over here, the rail is fine. There's nothing going on. But what happens here is I have a temperature flux. So I control my weld very carefully here, and I control my heat here. So the hardness of my rail here is about the same as the hardness of my rail here. The problem is outside of my mold or at the edges of my mold, I can't control the temperature so much. So I often have a softer spot, and that's where I see my weld batter. Now, the weld batter will grow and it will end up going to the center line of the weld as well, but it'll start off, you can see over here, it starts off in the heat affected zone. Even here, it starts off in the heat affected zone and then only grows and then expands in depth and expands in depth and length. As far as joints are concerned, I don't know if any of you have seen track like this. Believe me, there is track in Israel that looks like that. You go out to some of your yards and sidings, and it does look like that, even though this happens to be the United States and not Israel. You can see the batter at the joints. The batter is so severe that not only does it crush the rail, it actually degrades the ballast and sleeper underneath it. And this is one of the reasons why nobody puts concrete sleepers under joints. If you have to have a joint in concrete sleeper track, you need to put wood sleepers there because the dynamic forces are so high, they will actually crack your sleepers, going back to our whole discussion of sleeper cracking. And international practice throughout the world is if you have high dynamic impact forces, such as the joints, you can't live with your concrete sleepers. You either have to clean your joints up and make them perfect, which is a very difficult thing to do, or you weld them away and leave welds in there because the welds are stronger than the joints. So close-up look at the joints. This is the initiation of batter. You can already see, when I say initiation of batter, this is probably 10 to 12 millimeters deep. So imagine a wheel coming along here, hitting that, bouncing down, hitting that, we get very high impact forces. It's hard to see this batter here. Having trouble reading that depth. It's marked in here. This is a test that I did many, many years ago. This maximum batter is about 1.5 millimeters over a meter length. So you take a meter length here, the maximum batter is about 1.5 millimeters. But to give you an idea of the magnitude of the forces, look at the plastic flow. Look at the plastic flow on that rail. That's all plastic flow associated from high impact forces. Here's a close-up. You can see the degradation. You can see the plastic flow. You can see the start of degradation over here. You can see what's going to generate these very high surface joint issues. Now, this was a mismatched joint. So this was a mistake that somebody put in there. This joint, this rail, they use the wrong joint bar. This rail and this rail are a different section. And so you're supposed to use a compromised joint bar, which is what this is. But the rails are supposed to be perfectly even in the top, and they're not. So you can see what happened. You can see the plastic flow makes a little ramp over here. So the wheel comes along and up the ramp here, just all from plastic flow. Okay. Defects at rail connections. Talk some more about what happens at the connections themselves. So this is the rail surface defect. What happens at the connections? Now I kept saying that detailed fracture from shell is the largest category of defects in welded rail territory. In jointed rail territory, it's joint defects. Joint defects are significantly greater, which is why we weld rail. We weld rail because joint defects are so common that if you put in a significant amount of joints, you'll be dealing with joint defects on a continuing basis. Okay, so here's a classical 6-hole joint bar in good condition. Take off the joint bar, and we have our bolt hole crack. Okay, notice the bolt hole crack propagates at around a 45-degree angle. Why? Because the bolt hole combination is elliptical. And as a result, there is the contact stresses are maximum actually over here. And then they propagate. Now, the nasty part about this one is you can't see it because the joint bar is hiding that. That crack is happening behind that joint bar. So you only see it in one of two ways. You find it by ultrasonic inspection, which can see it, or the crack propagates out into the railhead and then you see it. This is a joint bar break. And in the process, you can also see joint bar wear. So you can see some of the wear. You can see the bolt hole crack. You can see the wear here. This wear is happening between the bottom of the railhead and the top of the joint bar, which is significantly weakening the joint bar. And then here we have a bolt hole break. We have a crack in the bolt hole. This is another nasty bolt hole break. You can see the 45-degree angle coming out. 45, this is not quite 45. This is more like 35-degree angle coming here. This one shows how it propagates through the rail, up vertically, trend down through here with a little side trip up to this joint hole as well. We also get cracks in the fish plate. Now, the good news, or the joint bar, by the way, I keep saying joint bar. For those of you who are used to calling it fish plates, fish plate and joint bar are the same thing, depending on which side of the Atlantic you want to call it. Now, the good news is most cracks in the joint bar are visible, but even better news is we're developing optical detection technology. And one of the first focuses of AI, artificial intelligence applied to optical detection technology, is this right here. And in fact, this crack was found by optical detection technology, where they were able to recognize the crack using AI of a video image. We talked about a pull apart earlier, and when we talked about thermal forces. There you can see the pull apart, the bolts are gone. I think that's one of the bolt pieces of the bolt right there. These bolts aren't going. You don't need to break both sides, just need to break one side so this can move. This is a nasty pull apart. Look at that. That's almost half my sleeper spacing. defective weld. Now notice again where my crack is. My crack here is not through the weld. My crack here is through the heat affected zone. Now, there are a lot of reasons why you can have a defective weld, and you get more defective thermite welds than you get more defective electric flash butt welds. But there are certain times where you just can't get an electric flash butt weld machine out there. And you have to use a thermite weld. You can have incomplete penetration of the weld metal between the rail ends. You can have lack of fusion between the weld and the rail end and metal. You can have entrainment of slag or sand, which gets caught in the weld. You get shrinkage cracking. When it cools down and shrinks, it starts to crack. And then you can have the good old fatigue cracking. So you can see you can use thermite welds anywhere at every level of technology. But if you don't quite do a good job of it, you can say that this has a little bit of porosity in this weld, I think we can safely say. And you can see this is very, very poor fusion, lots of air bubbles in this weld. This weld is not going to last very long. Okay, keeping on going, rail surface defects, mill defects. Deformations, cavities, or seams found usually on the surface of the rail, mill scale on the surface of the rail, introduced during the rolling process when you saw in the rolling mill. Most railways in the world that practice grinding grind new rail to eliminate the mill scale to make sure that there's no potential crack initiator on the surface of the rail associated from the mill scale. It's very common practice to grind brand new rail very, very lightly to do two things. Number one, to get rid of the mill scale, and number two, to put a better shape into the rail, a more specific shape. Because as we talked about profiles before, we want to change wheel rail contact, and wheel rail contact that we want to introduce in tangent track, shallow curves and sharp curves are different. So rather than trying to roll rail to different shapes and put them in the right place, which you know will never happen, because if any of you have watched the rail gang and work, you'll know that and guaranteed you have two different shapes that have to go, one in the tangent, one in the curve. You know that it'll go in the wrong place. So you have uniform symmetric rail that you put in place, nobody can make a mistake, and then you come along and you grind it to the shape that you want. So a sharp curve gets its shape, a moderate curve gets its shape, tangent gets its shape, etc. And you get rid of the mill scale in the same process. Give you an idea of some mill scales that you'll see in the rail. These are mill defects, sorry. Most of these, the big ones are found at the detection process in the mill. Remember all the sophisticated ultrasonic detection, that's what it's for, but every once in a while it's Greek screw. Okay, next defect, corrosion. I consider corrosion a surface defect, even though it's most common on the base of the rail, because it occurs on the surface of the base of the rail rather than internal of the rail. Most prominent wet and damp areas, tunnels, embedded track. You also see corrosion on track that runs next to bodies of seawater, oceans, saltwater lakes, seas. They're subject to saline corrosion. Metros are subject to electrolysis, stray current behavior, etc. Corrosion growth is usually a slow process, but not always. Again, can be accelerated by the power return, and it can result in a structural integrity and can also result in a crack that grows, as I showed you, a la Washington Metro. So
Can I
again,
have a question, please? Short question. What about the rust? Because I heard that rust can also protect the metal of the rail, or it's only due to corrosion.
Okay, well, the problem with rust is porous. So rust prevents the metal of the rail from if you have a rusting coating, let me take back. Rust in general is not effective. What railroad, for example, for railroads do, there's some railroads that are near seawater, that have a corrosion problem near seawater, will very often use some sort of coating in the manufacturing process on the base of the rail to put some sort of rust preventing coating, because you can see here, you can see how corrosion will penetrate. So corrosion means you have a rust surface, but you can see how it's penetrated here. You know, look what happens to your base of your rail here. So I for one have no confidence in rust being a corrosion inhibitor.
So actually what you say, rust always causes the corrosion.
Well, rust is a form of corrosion. To me, rust is a form of corrosion. Rust is an oxidation of the metal, right? Rust is an oxidation of the metal. Basically, that's what corrosion is. Corrosion is an oxidation of the metal, but it's a more aggressive form of it.
Okay, thank you.
Another defect, and by the way, we see this also in corroded rail a lot, is this sort of broken base behavior. Now, a lot of times we see this right around a fastener. So if we have a clip over here holding the rail to the sleeper, we will see this half moon type of break right around the fastener. Now, this is often associated with corrosion and thinning of the rail base, and the places where I have seen this the most are in tunnels. I've actually seen these a lot in mines. There's a lot of railroad in mines because usually most rail or cars run on railroad rail or mine rail, which is a smaller railroad rail. So you have a lot of railroad track in mines. So over the years, I've been called into mines a great deal to deal with mine track related problems. And I've seen a lot of these type of broken bases in mine type of track. Split web. Now, this is an interesting type of problem. The place that I most commonly experience this is when people are distressing the rail during the laying process, when they're putting the rail towards the right temperature. So when you distress the rail, you have to vibrate the rail to sort of shake it around so that the change in temperature that you're introducing, if you're heating the rail or if you're pulling the rail to introduce, to get you to your neutral temperature, your force-free temperature, you vibrate the rail. The most common method of vibrating the rail is to hit the rail with a soft hammer, usually a brass hammer. As a matter of fact, somebody asked me that question here recently. Some people have used plastic hammers, but they don't last very long. They're pretty soft. A brass hammer where the brass is softer than the steel works very well. The problem is every once in a while, somebody doesn't have a brass hammer and they get the brilliant idea of using a steel hammer to do this. And what happens when you do it with a steel hammer is you generate a stress concentration factor, a dent in the web of the rail, and it results in a split web crack. I had a case in Via Rail, the passenger carrying railroad in Canada a number of years ago, where they had a whole flurry of these split web cracks growing and then resulting in a pull apart ultimately because it was in winter. And it was associated with the contractor not having a brass hammer or a plastic hammer or a wooden mallet or anything soft to bang the rail with and hitting the rail with a steel maul and introducing cracks. And they had a whole series. I think they had 5 or 6 of them within a month of each other. Pop, 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 pop. Just not very nice behavior. Pipe rail is another defect. Now, this is not the vertical split head we saw in the head of the rail. This is a vertical split in the web of the rail from a totally different mechanism. What happens here is that during the rolling process, if there are any impurities in the rail, they get rolled into the web of the rail over here. And then under traffic loading, they form the seam. And then they actually will grow outward and fail. Now, the good news is this is more common with ingot steel than continuous cast steel. So ingot steel is the old-fashioned method of making rail, where you had ingots and you took rail from the top of the ingots on upwards. Continuously cast steel is where we're using continuous casters, such as you saw in the movie, is a cleaner process, has a lot less of these inclusions. And so this type of pipe rail is less common with newer rail, but we see it a lot in older rail. And the issue is most of the rail out in the railroad world is old rail. If I were to go through the United States, for example, I'd say that better than half the rail, and I wouldn't be surprised if, maybe 60% of the rail is pre-1990 rail, which means it was pre-continuous cast, pre-clean steel rail. And if you go, to a system that's an older system, the British, great example. I bet you 60 to 70% of British steels, the track and British network rails track, the steel is pre-1990 older rail steel. And you don't take it out just because it's old. It's too expensive and you don't have the resources. Another example of a pipe rail before it gets too bad.
Excuse me, can I ask a question?
Yes.
What do you mean by cavity in the ingot to unite in rolling? The last one. Yes.
Okay.
What does it mean?
Okay. So when you manufacture steel using the ingot process, you're manufacturing essentially 12-meter lengths of rail, one on top of each other. And then when you take them out and have shrinkage, you can get shrinkage in this behavior in this zone right here, where and so it says failure to unite means it's failure for this to form together. In other words, you get this type of behavior. You get this type of little shrinkage. This is a result of shrinkage in the ingot steel manufacturing process.
Okay.
Like I said, the good news is they don't use ingot steel manufacturing anymore. Almost all rail made in the world right now is made with continuous casting. But there's a lot of rail out there that was made under ingot steel. Okay, flattened rail, short length of rail, which has flattening across the railhead. So another surface defect. Okay. So let's go back and talk about how do we define defect size. Very briefly, I'm going to try to go through. I was hoping to get through rail today, but I may not be able to get through it today. I may have to spend a little bit of time next week finishing it up. But if you look at transverse defects, like the detail fracture from shell that we talked about, they're often classified by the percentage of head area size. Sometimes they're also classified by their actual physical size, but sometimes they're often categorized by their size, small, medium, and large. And very often when you find a defect due to ultrasonic inspections, if it's small enough, you don't have to remove it immediately. You can leave it in place and monitor it and follow remedial action. On the other hand, if they're medium or large, you usually got to remove it. It's all a function of the size. So this is taken from Israel Rail's rail defect standard. So you can see this is a transverse crack where they're actually using, instead of percent head area, they're actually using the height of the defect. And you can see there are three categories. Category 1, where this is greater than 25 millimeter, or this is greater than 25 millimeter. Category 2 is between 10 and 25 millimeters, and category 3 where it's less than 10 millimeters. So the actions are category 1, greater than 25 millimeters, get it out of there as soon as you can. And usually a slow order is imposed. Now in Israel railroad standards, I didn't see it here. If this was an American defect of that side, there'd be a slow order imposed, which means the trains will be slowed down to maybe 60 kilometers per hour until that defect is replaced. Unless you do something like reinforcing the rail with fish plates. Now, what can be done is if I have a defect here, like that, I can come in and put fish plates in here without cutting the rail and just put, if it's a 6-hole bar, I put 4, just the outside 4 bars, and this becomes what we call a safety strap. And I can leave that defect in there longer if for some reason I can't get it out there. So for example, Amtrak in the United States will sometimes do this because they can't get a gang out there to replace a defect quickly enough. Okay. Category 2 defects between 10 and 25 millimeters. These can be repaired with a time limit of 12 months. But again, very often a slow order is imposed. Again, in the US, a slow order would have been imposed, maybe 100 kilometers per hour slow order. In category 3, the smaller defect, no action is required. These just have to be inspected on a regular basis to make sure they don't grow into a category 2 or a category 1. Now, so we've talked a little bit about how a defect, and we've talked about a fatigue defect having, let's do a transverse. So we talked about a fatigue defect growing from a very small shell into a large 10-foot defect. So if you actually look at crack propagation in a defect, and we'll talk about this also when we talk about wheel defects as well as real defects, we have 2 phases. We have an initiation phase and we have a propagation phase. The initiation phase is when the defect basically grows to invisible to barely detectable. Barely detectable means I still really can't see it under my ultrasonic testing because my ultrasonic testing is not reliable at defects less than between 5 and 10%. And so that first phase of my defect is initiation. Then I start going into a zone where it starts growing more rapidly. And that's my propagation zone. So typically, the fatigue theory I gave you is mostly applicable in the initiation phase. And once you get into the propagation phase, I start going into crack propagation behavior. Now, just to give you the relative importance, if the rail life was the order of 1200 MGT, this initiation life would be about 1150. And this propagation life would be 25 to 50. So it takes a very long time to initiate and a very short time to propagate. I'm not going to go through the defect coding systems. Both UIC and Israel Railways have a defect classification system that's a function of location, where the defect is what it was caused by. So surface of the rail, so defects caused by damage to the rail, and what's the nature of the defect. We talked about this. just to show you some other definitions of defects and defect size. Longitudinal defects are always defined in terms of their length. You can see here, the transverse Israel Railways use it in terms of height. In many parts of the world, including many parts of Europe and the United States, it's percentage of head area. But everybody defines longitudinal defects in terms of the length. Again, head checking, squats. Again, you can see your squats. Bolt hole cracks, again, in terms of length. Okay. Maybe I'm going to see if I can get through Weibull analysis today. Let's see how time works. So, okay. So let me before I get to Weibull analysis, let me talk a little bit about how the relationship between wear and fatigue and maintenance. Now, this very complicated slide, it's a Weibull slide, and I'll explain what that is. So it's basically the amount of the probability that a rail will fail with a fatigue defect as a function of the life of the rail in MGT. This is all actual data. So and in fact, we're going to focus on this 5-degree curve, which was a test 5-degree curve at the test center, US Test Center in Pueblo, Colorado, where they were able to look at wear life and fatigue life both. So what they found was rail in this 5-degree curve. So a 5-degree curve is what? About a 1,300-foot radius, so about a 400-meter radius. So this 400-meter radius had if there was no lubrication whatsoever, and it was standard carbon rail with about a 320 BHN hardness, the rail life was it was about 100 million gross tons. Let's just say 100 million gross tons. And so there was never a fatigue problem because there was just never enough time for the fatigue to wear out, to fatigue to occur. So they went ahead and they put a piece of rail in there and they did a really, really, really good job of lubrication. And they dropped the wear rate by a factor of 10. So the wear rate went from 100 MGT to 1,000 MGT. Great. That rail is going to last 1,000 MGT. Wonderful. Well, not quite, because after about 200 MGT, they started seeing a development of fatigue defects. And between 200 and 300 MGT, they started developing sufficient fatigue defects as to have to consider replacing the rail for fatigue. So they never got to this 1,000 MGT, but they did double the 100 MGT life. They went from 100 to about 200 MGT, which is worth a lot of money when you double the life of the rail. Then they came back and ground the rail, because grinding is a technique to reduce the development of fatigue defects, and they extended the life of the rail to 300 MGT, which again, while not 1,000 MGT, was a lot greater than the original 100 MGT, and even 50% greater than the 200 MGT due to fatigue, due to non-ground fatigue defects. So you can see application of maintenance procedures can significantly extend the life of the rail, both from a wear and a fatigue point of view.
Alan, can I ask you a question?
Yes.
How did they manage to increase the first 100 MGT? What did they do?
Lubrication.
Lubrication. And then they grinded after
Yes.
that. Okay, thanks.
Grinding before lubrication usually doesn't save the rail fast enough. But then once you lubricate, you greatly reduce the wear life, then you can start doing things like grinding to address fatigue defect behavior. So that brings us to the issue of what is fatigue defects. And you know, it's 2 minutes to, and I really don't think I'm going to do justice to Weibull analysis in 2 minutes. So I am going to stop here. Those of you who want to look ahead, please do so, because I will be talking about the Weibull analysis, which is the most common method of predicting fatigue defects. Now, remember what's happening with fatigue defects. I have 100 kilometers of railroad, and I have one defect over here. Am I going to replace the rail? I'm going to replace this defect, but am I going to replace this 100 kilometers? No chance. And then I have a second, and I have a third, and I have a fourth. Oops. Can you all see, do you all see my screen sharing?
No, not now.
Okay.
You stopped sharing.
Yeah. What happened here? Okay, can you see it now? Can you see the Weibull curve, the rail
Yes,
fairy?
yes, I see it.
Okay, all right. Just remember, I can't see you when you shake your head, because when I have your screen up here, I have the screen up here. I don't see pictures of you. I have to stop screen sharing to see everybody. Okay, so what I was saying is, let's say we have 10 kilometers of track, just to make it a little bit easier. Okay, now it's easy to predict when to replace the 10 kilometers of rail, because when it's worn past your limit. But when do I replace my rail due to fatigue? Again, if I have one defect in 10 kilometers, I'm not going to replace the rail. If I have two defects in 10 kilometers, I'm not going to replace the rail. If over the course of a year, I have 100 defects in that 10 kilometers, I will replace the rail, because I'm never going to live with a condition where I have 10 kilometers per mile per year. That's way too great. And by the way, I have seen railroad segments with that high a defect rate. So it's not an imaginary number. So one of the issues becomes, when do I predict the rail, replace the rail? And then how do I predict it so that I know when to plan for rail replacement? So this now becomes a methodology of monitoring defects, collecting the defect data, predicting forward, and determining what's my rate of failure and when do I have to replace my rail versus fatigue. And by the way, I can also do that for wear, because I can predict my rail wear, and so I can find myself doing this kind of analysis. I can take my dry rail wear, I can lubricate it and predict my lubricated grade wear. I can predict my fatigue defect growth rate without grinding. I can predict my fatigue defect growth rate with grinding. And I can see which is my replacement point and when do I have to replace the rail. Why is that important? Because you just don't go out and replace 10 kilometers of rail when you say, oh, I want to replace 10 kilometers of rail. Number one, you have to have 10 kilometers of rail. And trust me, nobody has a spare 10 kilometers of rail. Nobody has a special extra kilometer rail. I'll bet you most systems don't even have an extra half a kilometer of rail flying around. You know, maybe you have 50 meters of rail here and 10 meters of rail there and 50 and 20 meters of rail there. But you don't have an extra half millimeter or half a kilometer or kilometer rail. So the first thing you do is you got to order it. Then when you want to install a kilometer of rail, that's not sending out 3 guys in a truck. Basically, a 12 meters of rail weighs close to a ton. So a kilometer of rail weighs 200 tons, right? So all of a sudden, you got to be a little bit more, you have to plan this stuff. And so the ability to forecast replacement becomes real differently. And I haven't even gotten into the economics yet. Okay, let's stop here. As usual, I talk too much. I can take a few minutes of questions. Next week, by the way, I'm going to warn you, I'm not going to take any questions because I'm on vacation and my wife's going to be sitting there yelling, when are you going to finish teaching? We're on vacation. So next week is going to be 9 to 1 sharp. No questions. This week, if anybody has any questions, I'll be glad to take a few right now. If you want to just digest it and come back next week, that's fine too.
Alan,
Yeah.
what is the 5-degree curve of the last?
A 5-degree curve is about 400-meter radius.
What it means? In
It's
this
about
case?
400-meter radius curve. Remember, we did this almost the second class. I thought you learned for a degree of curve. I
I know.
know degree of curve.
I know what it is, but what is the meaning in this graph?
It's a curve that's out in a railroad that has a radius of 400 meters.
Yeah, I know. Can you explain it again?
Okay. All right. So this is test data. This is actually test data from a couple of different locations. The 5-degree curve is a 400-meter radius curve. That was a test curve that was tested very, very accurately at a full-scale track test facility in Pueblo, Colorado, in the United States, called the Facility for Accelerated Service Testing, or FAST track. In that track, there's a 8-kilometer loop that's where basically a 10,000-ton train runs around in circles all day, every day. So it puts up about it puts up about 20 million gross tons a month on that track. And they use that to look at rail behavior and wheel behavior. So they can measure rail wear. And so they can actually measure how long it takes before the rail reaches its replacement limit dry. Then they can put another piece of rail in there of the same type, lubricate it, and measure how long it takes lubricated. They can also see when fatigue defects develop. They can grind it and extend the life of the rail. So that's the 5-degree curve we're talking about. We're talking about this test curve in Pueblo, Colorado. That's a 400-meter radius curve that has been very, very accurately mapped. So we know these numbers are very reliable. Did I answer your question?
What is the tangent 300 MGT?
That's another location where they have some other data. So here the fatigue. This is the fatigue. This is a fatigue point in the 300 millimeters. It's a different piece of track that I wasn't talking about in this example. And in fact, this is also a different piece of track. This is the Union Pacific Railroad data from the Union Pacific Railroad. But I was focusing on this 5-degree curve because it had a very nice story. All of this data down here is from this one test curve.
Okay, thanks.
There's a huge body of data out there on rail wear and rail fatigue. The biggest test tracks in the world are the Russians have a very, very large test track outside of Moscow. I've never been there, but I've had colleagues who have. The Chinese have a very, very large test track outside of Beijing. I have been there. The Americans have a major test track in Pueblo, Colorado, and I've been there hundreds of times, extensively. I was very actively involved in planning tests for that for years and years. The Germans have a smaller test track, and the rest of the Europeans don't have as many major test tracks. The 3 big test tracks in the world are the Russians, which I think is the biggest, the Chinese, and the American. Those are the big 3 in terms of big loops where they run trains around in a loop, and just to look at how components fail and how do you develop better components and how do you increase axle load so that and what components can stand under increased axle loads. There are literally thousands of reports. I go Google FAST, fast track, and the reports. Let me clear that. And this is one of the reasons why I'm drilling you all this North American terminology and all these PSI and pounds and degrees of curves and everything else, so you can go to this massive body of English language literature. And I'm talking about hundreds and hundreds of really specific reports about rail and sleepers and wheels and fasteners and ballast and subgrade failure and geotextiles and you name it. They've done it because the fast track was built in 1979, if I remember correctly. I was involved with the initial design of the fast track back in the late 70s. So it's been around for the better part of 40 years. And what you can learn about rail and track behavior is fascinating. So, and a lot of it is publicly domain. So you Google it, you go find it. And if you have trouble, let me know. They actually have a website. Well, the website is TTCI, Transportation Test Center, Inc. They have the website. The fast track is operated by TTCI on their facility. It's actually a U.S. government facility that's operated by TTCI, which is a subsidiary of the AAR. But the amount of information now, there's not a lot of metro information there. There's, unfortunately, there's some metro track, test track, but not in the fast loop. So it's more vehicle oriented than metro oriented. But there's a wealth of railroad information there. Okay, any more questions? All right. Try to look at some of the problems that I've given you, some of the class assignments. Anything that I've spent time in class, you can expect to see in the exam. I believe the exam, well, we'll talk about the exam later. We're still far away from the exam. But I never think my exams are hard, but then I know the material, so it's obviously not hard for me. I don't go out of my way to look to fail people, though. I look very hard to make sure that everybody pass. My goal is that everybody in the class will pass. I actually disagree with the Technion. They expect a certain amount of failures. I don't. I expect no failures. And I'm very, very disappointed if somebody fails any of my exams. So we'll get to that another time. Okay, I will see you next week from my hotel room. We'll talk, we'll finish up Weibel. And although there's a lot more about rail, and in fact, there are a whole bunch of additional notes that I'm not going to get to yet, but I'm going to, because of time, I want to tend to track train dynamics and track geometry, because I think there's a whole lot of interesting stuff to do. And I have some absolutely amazing movies on track train dynamics, which are not on the which are not the British rails. This is actually some Canadian movies that I got from some friends of mine that show some amazing dynamic behavior of the track, of the vehicles on the track, that I think you'll be fascinated in seeing. So again, something to look forward to for next week. We'll see you all. We'll see you all next Tuesday. Bye bye now.
Bye. Thank you.